Our next presenter is with Hach, and his name is Carlos Williams, and he will be talking to us today about continuous monitoring for nutrients. Carlos, go ahead, take us away.
Thanks for the intro, Travis. Appreciate it. So we are going to talk about online chlorine analysis and some of the differences between the two main styles of chlorine analysis, colorimetric and amperometric analysis. So what we'll talk about in this short video is a better understanding of the differences between these two styles of analyzer, the colorimetric and amperometric chlorine analyzers, and about why to select one type of analyzer over the other, and ideally to give you some increased confidence about how to pick the right type of analyzer for your application. The first thing we probably ought to talk about are the methods, because there are two main methods for reporting chlorine numbers. Some people out there don't need to report their numbers, but if you do, you need to use one of two methods. There's either the standard methods, 4500 CLG, so that's the DPD colorimetric online method, which is actually the same as the grab sample method. The colorimetric determination of chlorine, it'll collect the sample, it'll do a batch analysis, so it will take the sample in, stop the flow, add the reagents in the buffer. If there's chlorine there, it'll turn pink, and then it will, the deeper the color, the more chlorine that it has. We'll talk more about the analysis in detail, but for many, many years, for decades, this has kind of been considered the gold standard in chlorine analysis, both in the lab and also in process for continuous monitoring. The other method, EPA method 334, is more recent. It's for amperometric continuous chlorine analysis. It uses a continuous flow rather than a batch analysis, and it has a more recent approval. It was accepted by the EPA in 2009. So one thing to remember is that analyzers themselves, when it comes to regulatory reporting, analyzers are not approved. Their equipment is not approved. Methods are approved. So bear that in mind whenever you're selecting an analyzer. It's not the analyzer. You just have to pay attention to what method that analyzer is running and know whether or not it's an approved method. So I'll go over the principle of operation of the two styles. So the colorimetric analyzer, first it does a 0 and then it does a read. So it does two steps. This is the same if you're not familiar with a colorimetric analyzer, but you're familiar with the lab test. In principle, it's the same thing. You do a 0. It compensates for anything that might scatter light or might absorb light that's in the sample before you add the reagents, and then it does a read. So first it does a 0 on the sample coming in, then the buffer and the indicator are added. Once the color is developed that there's chlorine present, it measures the light transmitted through the sample at 510 nanometers. That's the wavelength of light that's used, and that's also part of the approval and the approved method. So the color intensity is compared to the calibration curve that's done with reference standards that's built into the analyzer. And then the last step is the sample cell is flushed and cleaned with a new sample before it's reacted with the next round of buffer and reagent. With an amperometric analyzer, the science or the type of analysis using amperometry is an electrochemical technique, and it measures a change in current based on how much chlorine is in the water and how it reacts with the electrode. So there's subtly different styles of this type of analyzer, but the electrodes are covered either with a membrane cap that contains an electrolyte, or there's an electrolyte of some kind that's or a buffer that's added that comes from outside the analyzer somewhere. We'll talk more about that. When the chlorine reacts with the electrode, there is a current that's generated, and that current is proportional to the chlorine concentration. This particular model that's shown on the screen is the Hach model. Excuse me. In 3 electrode systems, which is what this has, you actually have an anode that's split into 2 parts. It's got a reference and a counter electrode. Having that design allows for a more stable probe and more stable readings over the life of the probe, and it also gives the probe a longer life. So we'll talk a little bit about how these two methods of analysis compare. So in the batch process there on the left in orange, it measures an absorbance. So when we shine light through a sample, the more color that's in that sample, the more light gets absorbed. So the deeper the color, the higher chlorine concentration. On the right, the amperometric is a continuous measurement compared with the batch measurement in the colorimetric analyzer. So the continuous measurement is always measuring an electric current. The larger the current, the higher the chlorine concentration. We'll talk more about those differentiators at the bottom in a little bit. So to talk a little bit more about some of the things to consider when you're trying to figure out which one of these you want, whether it's amperometric or colorimetric, is to look at the speed of response. So what this graph is showing in the blue line, that's a step change in chlorine feed. So it goes from 1 to 2 milligrams per liter. And you can see it just goes, it's basically instantaneous. It just goes from 1 and spikes all the way up to 2. The red line is the response of the DPD colorimetric chlorine analyzer, and the green line is the response of the amperometric chlorine analyzer. So what you can see is that it takes longer, if you can see that red line, right? So again, the y-axis is concentration, the x-axis is time. So you can see that red line goes across, keeps going, doesn't look like it's responding to anything with the step change in the chlorine concentration until it hits about 300 seconds, and then it spikes up and it hits that exact concentration of 2 milligrams per liter. If you look at that green line, you see an immediate response. The only thing is that you also see that it's not giving you the 2 milligrams per liter right away. You see it start to increase because it's a continuous measurement, but it actually doesn't get to the exact right concentration until it gets to about 2.5 minutes. So either way you slice it, whether you're looking at a colorimetric analysis or whether you're looking at an amperometric analysis, to get it to the right concentration takes about the same amount of time. However, if you want to see something respond immediately, the amperometric is going to respond more quickly. To dive a little bit deeper into this idea, so we're looking at a T90 and a T100. So the T90 is the time that's needed to reach 90% of the expected change in the parameter concentration, and the T100 is what it takes to get to 100% fidelity for measuring the real concentration 100% accurately. So you notice that the T90 is about 100 seconds. That means to get to 90% of the chlorine concentration. And again, we're looking at continuous chlorine monitoring. This is just the amperometric sensor. This is not the colorimetric style of analyzer right now. So we get to the T90 at about 100 seconds. We get to the T100 at about 150 seconds. So now to talk a little bit about the differentiators. So if we look at the batch process analyzer is the colorimetric analyzer is largely unaffected by sample parameters like pH, temperature, chlorine concentration, flow, and pressure. There is a flow rate range that's required for this type of an analyzer, and that analyzer will, a lot of the analyzers will tell you when you're at the right flow rate. If they don't, you just need to be sure that you have a flow meter somewhere where you can look and see if the flow is correct. Temperature, it's unaffected. Chlorine concentration, it won't do anything. If you go over the range of the analyzer, it'll just peg out at the high range, and you can set alarms for that. And flow and pressure, largely unaffected as well. pH is not affected because there's a buffer that keeps the sample at the proper pH for the color reaction to happen. The colorimetric analyzer also does not require calibration. So I have a statement or a caveat right there. The technology does not require calibration. There are certain places in the United States and maybe in other parts of the world that require calibration, and that's mandated by the regulatory bodies in the state. The states have primacy, so if they say you have to calibrate, you have to calibrate it. But the technology does not require it. Just like when you run a manual test for chlorine, you don't have to calibrate your benchtop or your portable instrument. Those don't require calibration. You do a zero and you do a read. So you do a comparison measurement, and that concentration is read by the calibration that's already built in the analyzer. The amperometric measurement doesn't require chemical reagents except for that electrolyte, right? So I do put the asterisk in there to, whether you got the electrolyte in the membrane that needs to be changed every 3 to 6 months, depending on the pH of the sample that it's continuously in contact with. And then it also does need to be calibrated periodically, and that will be dependent on the application. It'll be dependent on the pH. It'll be dependent on the flow and pressure. To some extent, it can be dependent on temperature changes. And you typically will calibrate those with a portable or a benchtop DPD device that's colorimetric. So pH can cause big differences in the two species of chlorine that result from mixing chlorine with water. So the two species I'm showing you here are on this graph, HOCl, which is hypochlorous acid, and the OCl minus, which is hypochlorite ion. So note that you've got a graph here that has two y-axes. The one on the left is for the hypochlorous acid. The one on the right is for hypochlorite. And note that their scales are inverted. The hypochlorous acid goes from 0 to 100, and the hypochlorite goes from 100 to 0. So, and this shows you how pH changes. This shows you how concentration changes, or the distribution of hypochlorous acid versus hypochlorite as the pH changes. You can also see that there is a shift depending on the temperature. So all of these things, pH and temperature, will have a major effect on the hypochlorite and the hypochlorous acid. The reason why I mention this is because in a colorimetric analyzer, it doesn't really matter what species that you're trying to look at, because the DPD chemistry reacts with hypochlorous acid and hypochlorite. However, when you're talking about an amperometric sensor, it makes a big difference because the sensor itself only sees, quote unquote, hypochlorous acid. So we need to do something to convert all the hypochlorite to hypochlorous acid. And I'll talk a little bit more about that in a subsequent slide. So here's an example of how the pH is influenced. So the important thing to note here at the top of this table, this is uncompensated pH compared with concentration reading. So for free chlorine concentration of 1 milligram per liter, it's showing us 3 columns with different pHs. We notice that the DPD, it doesn't change. pH 7, pH 7.5, and pH of 8, they all read 1 milligram per liter, or 1 part per million. If the pH is not compensated for with the amperometric sensor, at pH 7, we read 1 milligram per liter, which is what the actual concentration is. At a pH of 7.5, we read 0.6, and a pH of 8, we read about 0.2 milligrams per liter. And this, again, goes back to the distribution of hypochlorite versus hypochlorous acid that I showed you in that last graph. So we have to compensate for the pH in some way. So either we use external buffer that's added from a separate carboy that's pumped into the analyzer, an internal buffer, or some sort of mathematical concentration, some other sort of mathematical compensation done by a pH reading or an entered pH. We also have to compensate for the temperature. So here, the pink line is showing you how the temperature changes. That black line is showing you the amperometric chlorine sensor and what it reads when the temperature is not compensated for. And then those red triangles are the colorimetric measurement. So this, again, is uncompensated. So this is what would happen with the chlorine concentration. Even though the chlorine concentration is steady, this is how the amperometric sensor would read if we didn't compensate for the temperature. So we have to correct for that. As we can see, it goes from about 1.5 up to about 3.5, even though the actual concentration doesn't change because the temperature changes. We also have to compensate or pay attention to the flow. So here again, we're seeing a graph. Chlorine concentration is on the y-axis, the flow is on the x-axis. So as we see a steady increase in flow from about 0.6 liters per minute going all the way up to about 1.7 6 liters per minute. We have a steady increase in our chlorine concentration. Again, the chlorine concentration remains steady, but the way that the analyzer or the sensor reads, it will read up to about 3.1 milligrams per liter, which is about 1.1 milligrams per liter over what the actual concentration is. So amperometric sensors tend to drift. The colorimetric analyzers typically need to have their reagents changed every 30 days. And at that time, they can also be cleaned. Tubing can be changed if necessary. That doesn't have to be done every 30 days. But the amperometric sensor needs to be cleaned and periodically, and it also needs to be calibrated. So we can see what happens here. In the pink is a colorimetric chlorine analyzer, and in the green is an amperometric sensor. If we don't calibrate it, we see these numbers drift down. That's what we see happening. And again, this is an uncalibrated sensor. If we calibrated it, it would remain steady. So with samples, we need to have a stable sample. If we want to use amperometric sensors, so stable sample conditions, static applications are best for the amperometric sensor. So regulatory and reportable, sometimes with process control you can have in static applications. Some are less static, some are really dynamic. The main point of looking at these characteristics for sample stability is the more unstable the sample is, the more often you're going to have to calibrate the amperometric sensor. The colorimetric sensor doesn't really care about how stable the sample is regarding pH, regarding pressure, regarding flow, also whether it gets chlorinated water all the time. That can affect the amperometric sensor as well. So just to wrap up, the colorimetric analyzer is accurate without calibration. It's largely unaffected by sample parameters. The colorimetric analyzer is not reagentless and it's not continuous. It does a batch analysis. The amperometric analyzer, it is a continuous measurement, as has a fast, continuous response to chlorine concentration. It is reagentless, so no reagents go into the waste stream. But the amperometric analysis is not independent from changes in things like pH, concentration, temperature, flow, and pressure. All of those things can have an effect on how the amperometric sensor reads. It's also not accurate without periodic calibration. So back to the last slide that I was showing you, make sure you look at the stability of the sample. I was showing you all those things because the less stable a sample is, the more you're going to have to put your hands on an amperometric sensor. And if it's someplace that's in a remote location or something like that, it may not be the best place to put it. So we can go through choosing your sensor. So step 1, take a look at the concentration range and the sample pH range. Step 2, I won't read all these to you, but look at the limit of detection and limit of quantitation, and also the response time, as well as the regulatory method you might need. Then also take a look at the different influences on your sample analysis, whether or not you want to calibrate, what your routine maintenance might be, and what works for your application. And then if you can have reagents in your discharge or not. And then which is more cost effective. You have to look at the total cost of ownership and the life cycle of the analyzer. And that's it. So I'll just wrap up by saying the best choice of the chlorine analyzer is really based on the application you have. Thanks for your time and your attention.
Fantastic presentation, Carlos. Thank you very much. For all of you out there who would like additional information on what Carlos had just covered, please feel free to visit their website at hach.com. And of course, more information can be found right here on wateronline.com.